Hello everyone. Our today's topic are materials data. As you will see, I have brought a few issues, topics, transparencies with me that you have seen already, just to remind you what we have discussed, but also to put them into a different context. So what you have seen the last weeks was basically many different tools of artificial intelligence. So you have been discussing big data-driven science. Today I like to switch gears and ask the question, where do we get the data from such that you can make these tools really valuable and give them predictive power? So before that, let me just recall what you did the last weeks. We have seen that there are many different fields that produce artificial intelligence tools, be it chem informatics, which is an old field. Of course, computer science is producing a lot of different tools, but there are also others from linguistics, from social media, from signal processing, just to remind you what we have heard about compressed sensing and similar methodology. All these fields have created a lot of tools, and this is what you have seen during the last weeks. Now, let me go to my topic of today. As I said, I would like to discuss a few things. First of all, materials data. In this context, I would like to introduce the 4V of big data to you. I will also talk about fairness of data, in particular interoperability and reusability, or recycling if you like. In the center of all this are metadata, the description of data. And finally, I like to give you an outlook where the field can be going when you put together these artificial intelligence tools with the proper data, fair data. So, first question, what are our data and where do we get them from? Let me remind you that materials science is a very, very big and diverse field. Materials are all over the place. There is hardly any point, any aspect of our society that is not concerned with materials. So think about your cell phones, think about your TV screens, think about the lighting. You need materials that have very good optoelectronic properties. Think about tools. You probably would like to have hard steels or other materials that are hard enough and tough enough in order to be useful for this. Think about our means of transportation, where we need materials that are light, for instance, in order to save fuel. But, I mean, you name it. There's other things like magnetism. You still may have a hard drive in your laptop where you need good magnetic materials. You need just metals that are good wires for transporting current. Or if you like gemstones, don't forget, this is also a very exciting field. Last but not least, of course, also medical devices depend very largely on new materials, on novel materials. So if you think about artificial hips or teeth or whatever. So you can think of that materials are very diverse. Of course, also all the properties are very diverse. We have just seen for some of the materials, hardness, strength, elastic properties are important. For others, their behavior, the light-matter interaction is important. For others, magnetism is important. For others, again, biomimetic materials are important, such that the body doesn't react to them if they're implanted into the body. So the field is very diverse, but also the data themselves are extremely diverse, and that's why I would like to spend quite a few minutes discussing what the materials data are about. So to do so, I like to start with the 4V of data, and with this I start with the volume. This is the amount of data. The second V is the velocity. This is the rate at which data may arrive or may change. Then the third V is the variety. This is the heterogeneity of data and the form and the meaning of the data. And finally, the veracity. This has to do with data quality or the uncertainty of the data quality. Before I get to materials, I would like to take another example into account, and this is data that come from, for instance, astrophysics or collected at the Large Hadron Collider at CERN. As you see here, I don't discuss volume and velocity separately. They somehow come together, and for some of them velocity is an issue, for the other volume, but very often we have to discuss them together. And this is the case also for the LHC data. So what CERN explores is collisions that are in the order of 600 million collisions per second, right? So the raw data for each of these collisions, so this is one event, comes with 1 megabyte. This is not too much, but thinking about 600 million of them, and if I did the math correctly, this finally ends up with something like half a petabyte per second. So there's no way that people can record all this, and there's no way that people later on can inspect all this. So we have to take decisions on the fly. And so finally, what is important for the researchers there are probably 100 or 200 events per second that are of really interest, and they are processed at the rate of 1 gigabyte per second. So, as said, people need to decide and elect and compress on the fly, so there need to be algorithms and data centers that do all this such that at the end a reasonable amount of volume, reasonable amount of data is stored. How does this compare to materials data? Now, I just pick one example. This is an electron microscope, and in fact you will probably hear more about electron microscopes later when Christoph Koch is going to give a presentation about experimental material science. But just to give you an idea what type, or not what amount of data is produced here. So this is approximately 7 terabytes per hour. And this, of course, does not sound much, but overall, if you consider that, or compare this to the amount of data that is stored in CERN, this is exactly the same order of magnitude. So, but this is just one microscope, and then consider that there are many instruments on this planet. The volume of data is extremely high. However, it's distributed, so it's not that you don't have to take decisions on the fly, so you still may store the data and inspect it later on. So in this sense, it's easier to handle. So speed is less critical because we can record this data, and we also have to consider that instruments don't typically work. They're not operated 7 days a week and 24 hours. But researchers work there probably for a few hours a day, and probably not even every day. So in that sense, the volume is enormous, but speed, velocity is not critical. What about theoretical data? And this is a transparency that you have seen already. I just want to remind you on the data that we are creating here. So input is a small data set. But then if it comes to, let's say, advanced methodology, we produce data that are enormous. And in particular, I want to point out two methods. One is molecular dynamics, also ab initio molecular dynamics, as you see here, that just from one single calculation, we may end up with terabytes of data. So how to deal with this? Likewise, many-body perturbation theory, so the advanced methodology to describe excited states also comes with enormous amount of data, because here we have to handle non-local operators, and these are mathematically, conceptually, but also numerically extremely demanding. I'll show an example in a minute, but again, so to compute such matrix elements, for instance, very easily, you can create terabytes of data just for one material. So how do we deal with that? One thing in particular for molecular dynamics is we don't probably need to store every point in space or time on the trajectory, but we can selectively store the data. For many-body perturbation theory, but also for other theories, we may consider to recompute data if needed. So in particular, if it takes a lot of time to store the data, but even more time or the same time to read out the data again, then we have to think about whether recomputing is more efficient than storing and retrieving the data. In particular, in view of the aspects that computers will become faster and faster, such that recomputing may be easier in future times. However, we also have to think that there's a drawback, because in order to get exactly the same data recalculated, you need the same code version, and probably even the same parallelization tools and machines in order to be sure that the data are the same that you have lost at some point. So let me move on. After talking about volume and velocity, let's have a look at the other two V's. These are variety and veracity. And again, I put these two together because somehow these two go hand in hand. Here, as you see, I also have brought a figure that I have shown you once already. And this is a collection of optical spectra of one material. This is what I say here. These are samples that are called silver because, as pointed out already, if you just compare these different results here, they don't look even very similar. So it's not that we talk about differences in the peak positions in the order of milli-electron volts. So here I think we're talking about a range of at least tens of an electron volt or even electron volts. So you wouldn't consider by just looking at these different graphs that these materials are the same. So and here the veracity comes into play, namely the veracity coming from different sample qualities. So obviously different samples have been used here, and as we all know, samples are not perfectly clean, they are not growing always as single crystals, but they come with dirt, and of course every dirt somehow concerns the research results and the quality of the data. But what else? It's not only the veracity coming from the material itself, but there's also a variety coming in, namely there's many ways of obtaining the same quantity here, which is the dielectric function in this case, from different experimental means. There's ellipsometry, which gives you the dielectric function. There's absorption spectroscopy, so most of this data shown here are taken either in absorption or in reflectance spectroscopy, but there's also electron loss spectroscopy that can be used in order to get the same quantity. However, I like to emphasize again, so in neither of these methodology here, you get as a result these curves directly. So there's always some transformation steps involved, there's also some modeling involved. And this not only comes with the variety that we have here in terms of methods, but this also adds veracity, because all this modeling behind and going from the raw data to the transformed data has some approximations and some limits. So needless to say that we can also compute the same quantity on various levels. So just to remind you, you just can do a simple DFT calculation with a very simple functional and then just compute the independent particle response to this. You can do this by using more sophisticated electronic structure, for instance by GW. You can use time-dependent density functional theory to get the spectra, or you can use the solutions of the Bethe-Salpeter equation, which should give you the best possible answer to this. So all this is not only variety, but again, veracity. So for each method, we have different instruments. If we talk about experiments, every instrument comes with its own resolution. Different vendors have different data formats, different ways of processing data. We have, from the theory point of view, different computer programs. They implement different methodologies, different approximation, different numerical aspects. And overall, all this adds to not only variety, but to veracity. So I mentioned GW as the example for computing electronic excitations. And also I have shown you this picture here, but let me just remind you how different you can implement one and the same method. Right? So GW means it's not an abbreviation for something. GW is the product of the Green's function and the screened-Coulomb interaction. So if you start to compute this, you would start from computing the Green's function, and this Green's function, of course, needs as an input some wave function, single particle wave function, and this you would take, for instance, either from a Hartree-Fock calculation or more probably from a density functional theory calculation. So obviously the quality of the ground state will enter here already the first guess of this Green's function. Now from this Green's function, you can, of these non-interacting particles, you can compute the Green function of the interacting particles by solving the Dyson equation. And here you can do this in very different manners. So you can just use the so-called single shot G0W0 approach. You can do some kind of partial self-consistency. You can use quasi-particle self-consistency. You can use full self-consistently. So there are many, many different approaches, and these different approaches also come with very different approximations and very different numerical implementations. Now jumping from here, what you else need in order to get your final result is the polarizability, which is a product of this Green's function. So needless to say that the approximations that have entered here also impact the polarizability. But you can also use very different implementations. So you can do it in the random phase approximation, you can sum over states, you can solve the Sternhammer equation, you name it. So I'm not going into every detail here, but you see already from these very few examples how big this manifold is of obtaining one and the same quantity. Well, just quickly going on. At some point, you have to consider whether you would like to take vertex corrections into account or not. And finally, the wanted quantity at the end is the self-energy, because this gives us the quasi-particle energies, and the self-energy, as said already, is the product of the G and the W. But also here, there are many different ways of implementing that. So, in one word, all this enters the quality of a calculation. It's not only the approximation, finally, it's also the numerical issues that give rise to accuracy on the one hand, the accuracy of the method, and the numerical precision of the implementation. Apropos numerical implementation, I also want to recall the paper that I have already pointed out before. This was a community effort to check whether, given you use the same approximation, all the different codes would get the same answer. You can look it up in the presentation that I've given at the very beginning of the conference or of this lecture. But I'd like to recall you that we have to distinguish between the precision of a numerical implementation, and this is actually what was tested here, and the accuracy of the method, like I've just pointed out with the example of GW. So, in essence, and this I think is very important, we won't change the situation, right? So we won't change the situation that people will come up with new methodology, that people will implement methodology in different ways, that people will do different approximations. I think this is also very, very important for our scientific development. However, in order to make data meaningful, we have to describe them. You have to tell the users of this data what these data actually mean. And this brings me to the next topic, to the next aspect, and this is actually the metadata. So I may stop here for a second, and you have the opportunity to ask questions if you have. So let us continue. As I said, we won't change the situation. Physics data and materials data are very complex, and also our theories and our experiments need this complexity. However, as said, we need to describe the data very properly. And in fact, this is also a transparency that you have seen already. I really want to re-emphasize that in order to make materials data meaningful, this requires an in-depth description of this data in terms of how they have been obtained, how they are further processed, and so on and so forth. So in fact, we need to start from looking at the sample synthesis. As you have seen before, obviously different samples have created a different quality of data. So we need to record all the data at the instrument already when the samples are created. But then we need to record basically everything. So all the data of the instruments, they are characterized, and I think very often a material is characterized from very different means. Then of course we have to record all the measured data and also the experimental conditions under which they have been recorded. And then we also have to take into account how this data evolve. As I've said before, if you want to record an optical spectrum, you probably record something which is the raw data, but it's not the dielectric function, for instance, you're finally interested in. So the transformation of data is a very important process. The analysis is very important, and so on and so forth, until the publication. So from the birth of some data set until to the publication, you really have to follow this very closely. I come back to the issue of metadata again when I briefly discuss this theoretical data in a different context. And this different context is actually fairness. Now we have seen fairness already. We have already seen what the definition of fair is. Now I'm going to ask the question, how fair are we? So, to recall, fair stands for findable, accessible, interoperable, and reusable. This goes back to a formal definition that has been written down basically by Wilkinson and a lot of co-authors in 2016, and I think nowadays everyone or every different area wants to cope with these fair data standards of processing and handling of data. We can also use fair in a different context, so probably a little bit more, let's say, modern way of interpreting this fair, namely findable. Of course, this is very important, but A, I, and R may stand for artificial intelligence readiness. And this is probably something that you are more interested in, because this lecture is actually called Artificial Intelligence of Material Science. So how do we make data findable and artificial intelligence ready? And in order to discuss this, I would like to take another step back. So even before 2016, we go to the year 2011, and we like to see an event at this time that actually has boosted the production of material science data. So in other words, I've brought a guest with me, and this guest we haven't seen for a few years now, Barack Obama. He was a president in 2011 when he launched the so-called Materials Genome Initiative. As you may know, every president of the US has some important program for science, and the program of Obama was this Materials Genome Initiative, MGI. And the idea was to open up material science, but not only this, he really wanted to give it a boost by helping the business. So he was not an enthusiastic scientist, and his heart was not burning for doing experiment, but he really wanted to support industries and support business in order to get faster from the development or from the detection of an invention of a material to bring it to the market in terms of products. But he boosted the field of material science, and many different databases since then have been established, and many high-throughput initiatives have been created since that. So very interestingly, a few years later in 2015, he even said that data underlying scientific publications are not available for confirmatory analysis, reuse and repurposing is an anachronism that we aim to address. So he really asked for sharing data, for making them public, because only then we can reuse the data that have been probably produced for a different context. I come back to this. And we can also reanalyze them and see whether we can confirm our own data or the data of previous times. So, and as I said, this boosted a lot of high-throughput initiatives and also many databases. I mean, there have been databases already before, but this gave it, as I said already a few times, an additional boost. And I would like to show you a few examples of such databases, such that you can get an idea what these databases are about, how they distinguish from each other, what are the aims, and what exists on this planet. This is not a complete list, but it actually at least a quite good collection. I mean, maybe the most prominent one, the most well-known one, is the Materials Project, started as a computational database, and as you see here, the aim is to compute properties of all known materials. So basically there is a lot of calculations there for structures that are collected in the Cambridge Materials database. Well, just to give you an idea of what kind of properties are collected, so there are properties and materials for batteries, for electrodes, for whatnot. So there are many different materials, classes or applications that this project has in mind. Elastic properties, mechanical properties are very important for them. Another database also computing a lot of these structures is AFLU. AFLU is probably the biggest one in terms of data that have been collected. As you see here, there are band structures, there are beta charge analysis, also elastic properties, thermal properties, a lot of phase diagrams also available. And this is actually what AFLU shares with OQMD. OQMD has very similar data, a little bit different focus. So you also see what OQMD offers in terms of phase diagrams, alloys, and things like that. Now, we also have discussed already the NOMAD laboratory. It's a little bit different than the others, and I come back to this aspect in that sense that you cannot only explore data that are sitting in such databases, but you can also publish your own data with NOMAD. In that sense, NOMAD is pretty specific. Well, what else do we have? We have Kasana here. This is a database that is created by the group of Rampi Ramprasad. Rampi will be one of our speakers in the next weeks. We also have, for instance, databases that are dedicated to a specific type of materials, like the Computational 2D materials database from DTU in Denmark. We have the Materials Cloud. Here, not only theoretical data, but to some extent there's also experimental data available. This database is hosted at the EPFL in Switzerland. I have an example here from a Chinese database, MatCloud. MatCloud also holds theoretical and experimental data, and so on and so forth. So as I said, this is not a full collection, not a complete collection, but it gives you some idea what is available on this planet. So you might be happy because obviously there's a lot of activities going on here, but you also may be scared because if there are databases all over the place and they really don't talk to each other too much, then you have to be worried about the following facts. So each data collection obviously serves a certain purpose, and I think this is great because every scientific community has its own focus points, and that's why we need to have variety in all this, right? So it's good, but as I said, leads to very different solutions. Of course, every database then uses its own or defines its own individual file formats. Every database defines its own metadata because there are no common standards yet, right? Every database has its individual search engine, and of course, a lot of effort probably could be avoided if more effort would be shared, but I think it's in the interest, of course, of different communities to develop what is very useful for them. Now, of course, then every database offers individual APIs for downloading data if this is wanted, so not all of them do, but many of them do. And so you may be scared that what about if I want to search for a certain material or for a certain property of material, do I need to go from one database to the other in order to find out whether there are data in a database that are of interest for me? So this might be quite tedious. And well, actually, there's an answer to this because there's an effort from the community, so that means from people running all these individual data collections, to offer the user community a common standard, at least a minimal common standard. And this is what the Optimate project is about. So the Optimate project started from a conference that took place where all the, let's say, key persons from different databases were present, and we all decided we should have an API that allows people to search all the databases at the same time. So, and Optimate now is, I think it's already available, so you can ask a question, you can send the query account to this Optimate API, and it will tell you in which database you will find the information that you need. So I think this is a very important community effort that goes in the right direction for us. So this is, for instance, a collection of, and probably not the full list, but at least you see the list of databases that are contributing, or some databases contributing to this. So let me just, before finalizing this part here, also remind you that each of these databases serves a different purpose. As we have seen, materials project, for instance, has a lot of material for batteries, but not only for batteries, for many more materials. AFlow, AQMD, so 2D database, all these, they have a different purpose in mind. In that sense, they are less critical what concerns metadata if you stay within this realm, right? So if you stay with all the data of materials project, there is no problem of comparing different data to each other, because materials project, as much as AFlow or QMD, they all use the same codes to run the data, so there is no veracity coming, or not so much veracity coming from this side here. So all the calculations, or most of the calculations underlying these databases, come from the VASP code. They're dedicated very often to very specific materials classes, and they don't allow people to upload data. So in that sense, they can control very well what the data quality of the database is, because they run their own calculations. Right? So in this sense, Nomad is different, because Nomad is really a crowdsourcing effort. As we know, since 2014, Nomad allows people from all over the world to upload data. and there are more than 100 million calculations already available in there. And this, of course, is a great effort. It's great because you really collect the big data that you probably need in order to fulfill finally our aims to have enough predictive power and to predict materials for a certain purpose, right? But at the same time, of course, it gives us a headache because you may ask the question whether you can combine calculations from these different sources. As I said, you can apply a machine learning method, you can apply your novel approach in artificial intelligence by applying it to data that you control very well and to know very well. However, you may not have enough data in order to have predictive power and go beyond what this database that you're using is really offering you. So in that sense, I think it's extremely important to bring together data from different sources, but it gives you a headache because you really need to ask the question about interoperability. Am I really allowed to use data from different sources together? So, and this brings me back to also a transparency that I've shown you at the very beginning, namely the NOMAD archive, where you see how many different computer codes have been used for the data that are uploaded to the NOMAD repository. So just in a nutshell, these are 40 different codes. The output files are fully parsed. And now I promised I get back to the issue of metadata. Of course, in order to do so, in order to have all this data here fully parsed, you need to have metadata not only that are generic to the physics, so there's not only metadata for energy and for elastic constants, but you need to have very code-specific metadata that tell you the difference between the total energy of exciting and the total energy of the WASP code, for instance. Now, talking about publishing, data here are published like manuscripts, so every data set gets a PDI, even a DOI if it's requested, and you can use the data. So download the data by the CC BY license, so like a paper. And then you can use all the data for your application of your artificial intelligence tools, if you like. So, of course, this is an international effort. That's, I think, quite clear. Now, also, when talking about fair means findable. Of course, databases make data findable, databases and APIs in particular make data accessible. The encyclopedia means showing what the results of the data are, makes data even human accessible. Just to complete the fair, the 4 digits in fair. Now, the last one actually is the R, and this is reusability, and I just call it recycling. And what I mean with recycling, I tell you after a few minutes break, where you again have the chance to answer questions. So, what about reusability? I'll ask the question, what do we do with our waste? So reusing data means not only reusing data, but also recycling data. And as you will see here from the next transparencies, I have become an expert of trash. And yeah, why I'm an expert, you see already that I'm able to separate different trash cans and different kinds of trash. And I will slowly walk you through these trash bins, and in order to explain you what this means, and also what you miss, or what the community right now misses by calling all this trash. So on the left we have a trash bin that is called synthesis recipes. So obviously, apparently, everything that is not successful is actually trashed. You may ask, well, probably it's a good reason, probably not. Metadata, so typically many notes are taken in even handwritten lab books, and there's a lot of stuff that is simply trashed. so being very useful in terms of describing data. The third category concerns candidate materials. These are materials that are not further considered because they turn out not to be useful for the purpose that I just have in mind when I do some research. And yeah, finally, what is the residual trash? Everything that is not used in a publication. So let's start with the left side and just looking into synthesis. So what I've shown here on the upper left is a very beautiful crystal. It's aluminum nitride for those who are interested to know what it is, and for those who are interested what the methodology is that has been used for growing it. This is physical vapor transport. Right? So this is a crystal that many people like to work with because it's very beautiful. It's a, let's call it a perfect crystal. Right? So this is a successful synthesis, the outcome of a successful synthesis, but still this synthesis recipe or this crystal may not be fully published. Either not published at all or not fully be published. And why is this so? Actually, there's several reasons for this. So, I mean, one reason would be that people didn't consider it important to publish it. The other reason would be a pretty human one, because sometimes you want to keep your secrets because this gives you a competitive advantage. So you can grow further crystals probably with the similar type, and then you produce very nice papers. Well, this is a reasonable reason, I would say, but in particular, it's even more reasonable for industrial research because there you really have a lot of competition, and it's clear that not everything needs to be published. But this is a different issue. I think we could discuss in a separate discussion. But there is also other reasons why people don't publish the synthesis. And very often because the metadata are not complete. So very often you don't know all the data from metadata from the growth procedure. Very often there's only handwritten notes on how you should grow a crystal, and very often also you just get some information in the corridor at the coffee break at the conference. So not everything is really written down in a reasonable manner. So that's one thing. However, even if everything is published and made available to the colleagues, this means that very often only, or most of the time, only success stories are published. And of course this leads to bias. If you only publish those things which are great and nice, you don't know why things fail or why things that fail, right? And that's why I've also brought a few examples of not so nice crystals. Actually, maybe they are don't look very ugly, but compared to the one on top, probably it's not the crystals that you would like to have. So in that sense, these data never are getting published. But this is a drawback of our community. I think we really should publish also failures, because doing so would reduce the bias and thereby also enhance our understanding. And also important in view of artificial intelligence tools that are less biased if you have data available from all different sorts of experiments. So, in fact, there is no comprehensive source of or database that contains synthesis relevant data. There's just something coming up now. There is a database or a collection of synthesis recipes that has been collected by scanning publications in view of the synthesis recipes. But again, here the bias is there, because even in publications, as I said, even if it's published, there are only success stories published. So that's one thing, and that's why I would say most of the information about synthesis basically goes to the trash. There's hardly anything available, but this would be very useful information. Let's go to our second waste bin, and this is metadata of experiment, mainly of experiment. So if you carry out an experiment, probably the student, the postdoc, the professor, they're all taking notes about how they measure things, also how they grow things, they synthesize things. So whatever measurements is done, it comes with metadata, be it from the instrument, be it from the notes of the person who has recorded this experiment. So whatever you do, there's a lot of information, and at the end you publish the paper, but this additional information is actually going to the waste bin. And of course the paper is still nice, the paper is still valuable, but you still may ask the question of how much value are the data if they are not annotated. So very often data are kept, so it's not always that the data themselves are getting erased, but only the metadata are not there. So data are there in big labs, in universities, wherever, but they're not annotated. And the question is, can they be ever useful if you want to get back to them and get information out of them? So just keeping the data because the funding agency tells you that you have to keep data for 10 years doesn't help. I think data are only valuable if you keep them together with the metadata. So recycle metadata or keep metadata. This is what we have to learn from this. Now, third category, candidate materials. So it's not only data or metadata that are getting lost, but very often even whole materials, material classes are getting forgotten. And so I like to remind you also on something that you have seen in the very beginning, and this is high-throughput screening. Now, how does it work? For instance, you would like to construct a solar cell, and you would like to know what materials are relevant for a solar cell. Then you have to think about the criteria it has to fulfill. So property one, probably most important, would be that the band gap of a solar cell needs to be in the order of, let's say, 1.4, a little bit less or a little bit more electron volts, right? Property two would be that the charge carriers need to have a high carrier mobility. Property three may be that the light-matter interaction should be very strong. Electron-hole pair energies should be small, and so on and so forth. So you can think of a variety of properties that you wish to have for a certain application, and then you just run your high-throughput calculations or experiment and just screen all kinds of materials for the purpose that you have in mind. So at the end of the day, you will see that in this case here, for instance, we found 3 materials that are very, very promising for this aspect, but there are thousands of materials that are not promising for that, and that's why you close the lid of the trash bin. And what happens after this, actually, these 3 materials, they are considered to be so important that they are taken to heaven, and everything else goes to hell. So, is this wise? Of course not. So this is not really trash. Let's recycle this. Let's get this trash bin back here, because whatever you find in here, so the materials and all the information about these materials is extremely valuable, but they're not valuable for this actually purpose of the research. So they're probably not valuable for a solar cell, but they're valuable for something completely different. So by no means this is trash. Let's recycle it, let's keep it in mind, and let's keep, of course, all the data related to that. So, and then finally I like to come to the residual waste. In German you would call it the Restmüll. And this is something that brings me back also to an aspect that I have addressed already, namely how we do physics today or material science today. And so, in fact, as you see, people all over the world, not only in my group, they're producing data, they're running calculations, they use a lot of computing capacity in order to run the calculations. The same is true, of course, for experimental investigations. At the end of a year or at the end of a PhD study or so, everyone is very happy to publish nice papers. But as I pointed out already, of course, publishing paper doesn't mean that you provide all the information or the insight that you have got during this research. So, again, I like to remind you, what you find in the publication is probably a table or a figure or a structure of the material or additional numbers that we have extracted, but it's never the full information. Now, of course not. Who wants to read papers that are 100 pages long, or who wants to write a paper that's 100 pages long? So I think the way we publish is perfectly okay, but still we shouldn't forget that probably the additional information that we have gained over these years shouldn't be completely trashed, shouldn't be completely forgotten. In that sense, our research is great, but it's not really efficient. It's a lot of trial and error if we investigate one thing after the other and publish one paper after the other about one material, about a few materials. So there still should be the way of bringing all the additional information together and keeping it somewhere alive. And just in a nutshell, what we find typically in a paper is, well, one publication, the result of several years of work of a person or more. It's the result of maybe several million CPU hours for producing one paper. And if you want to measure it in terms of data that you have produced, for sure this will be not only gigabytes but terabytes of data. And this data contain all the information that is finally probably not published. So in that sense, you may ask the question, is it worth doing again the same again and again? So should we ask the next student to run the same calculations? Of course not. That's why we are creating databases now. And this is the reason why we keep data. But still, I think for most of the calculations, this data is still going to the trash bin and still not recovered. So now, if you think about all the waste baskets that I have introduced to you, let's turn it into gold. Let's somehow do this. Let's recycle them. We make gold of it, because I think data are really a very important raw material of the 20th century. And by recycling the data, by storing the data in a meaningful way, we can really make use of this raw material. So, this brings me to nearly the end. As an outlook, I just want to summarize what we can reach in the community if we take all this, what we are discussing here, very seriously. So, I think the research of tomorrow, of course, still will consist of our daily research that we are doing, but it will be, let's say, have the fourth component, include the fourth paradigm of material science, of research. And I like to read this sentence to you because I think this somehow summarizes everything that I wanted to say. Namely, if and only if we build a comprehensive, fair data infrastructure capturing all aspects of data, from the synthesis to experiment and theory, and interweaving data, metadata, processing tools with novel concepts of artificial intelligence, then we can reach a new level of materials research. So this new level will have a lot of predictive power by the artificial intelligence tools that you or your colleagues may create in these years or in the future. So, of course, as a prerequisite for this, we need to change our culture, our scientific culture, also our publication culture. And let me at the end just show you a very old example of how sharing data actually can work or lead to something very exceptional. And this is the historical example of Kepler's laws, right? So Kepler and Tycho Brahe, they lived well, around 1600 or so. So Tycho Brahe passed away in 1601. He was the astronomer at the court in Prague, so he had very precious instruments. He was an experimentalist. He had very precious instruments to measure or to observe the movement of the planets, right? Kepler, in the last years of Tycho Brahe's life, he was a theorist and he was an assistant to Tycho Brahe. I put here a question mark to the history of sharing simply for the simple reason because during the lifetime of Tycho Brahe they didn't get along very well with each other, simply for the reason that they have different views on the scientific, let's say, picture of that time. You may call it they were not sharing their metadata standards, right? So they have different views on the thing, and that's why it was not there was no successful collaboration at that time. But still, I think it's very important that Johannes Kepler was allowed or was entitled to analyze Tycho Brahe's experimental data, and doing so allowed him to finalize the Kepler's laws. And I think this was really a breakthrough, and this was a breakthrough somehow by putting together data from theory and experiment, and I hope there will be a lot of breakthroughs that will come from sharing our data in the future. With this, I would like to stop. I also like to share my view on the library of tomorrow. So, of course, we will still publish our papers like we do. I think they will probably contain more information about the data. I think we still will have books as a fundament of our knowledge. But very important, the library of tomorrow will be very much enhanced by tools and by the data that the community is sharing and will be even more sharing in the future. And so I'd like to thank you for your attention for now, and you still have the option to ask questions if you have. Thank you.